This is Lab 2 on lines of charge. The purpose of this experiment is very similar to what was the case in Lab 1, so I'm just going to speak about the main difference. And the difference for Lab 2 versus Lab 1 is that in Lab 2 we are treating a piece of tape as a distributed charge as opposed to a point charge, and therefore one of the key purposes is determining the differences in the results for what we got in Lab 1 versus what we get in Lab 2. And just to get a quick insight into the key result, the tape that we get has a total charge of about 2.1 E-8 coulombs. So the key physics principles for this lab are almost the same as what's in the last lab, so I'm not going to go over the stuff on the left side. However, the distributed charges is new. So instead of doing point charges for the top and bottom tape, now we're going to get individual infinitesimally small pieces of charge called dq. And the value of dq is just the total charge divided by the total length multiplied by the change in length, which represents the dq piece of that total q. And so we plug that number into the total or electric field equation, integrate with respect to L, which is going to be y or x in this case, and then solve for q. So I'm going to skip over the procedure, though I gave you the diagrams and the values that we got for like mass and length and r, which is distance. And so for the key thing here are findings of the experiment, like hand calculations for the charge of the top piece of tape. We already have our formula that I showed you in the physics principles, k times q1 over r times root r squared plus l over 2 squared times r hat. That's for the electric field on a distributed rod. And so we plug that into the force equation by multiplying that number by q again, and we get q equals 2.137 E-8 coulombs. So as I mentioned previously, the key assumptions that I had to make was to assume that each U-tape had about the same amount of tape evenly distributed along the length of tape. This is because otherwise you just can't solve for stuff. And so that makes it, make it impossible to do the lab. And as for the coding, the key thing here is on line 122. When you start with the electric field, which is something that we just, or actually we do have to code ourselves. We can look at the right side here, the function for E field. This is using standard stuff that we copied from lab 1. But anyways, you start with that electric field at the top caused by the dq bottom, but then you have to multiply it by the top charges. Obviously, that's the difference between electric field and force. And you just do that for a bunch of different dqs along the line, and summing all those forces up gets you the total force. So as for errors in this lab, there was nothing that serious, so I'll just skip on from that. We probably overestimated the distance, the r value, but that's about it. So for what if we modeled each of our tapes as a point charge? Well, then obviously we get the same answer. And comparing the estimated value of the charge we get. Yeah, so in lab 1 we got a greater electric force, which makes sense, right? And as for answering the why there, this matters. Why do these estimates differ? That's because, well, now we care about the length, right? The length of the bottom piece of tape, or the top piece of tape, I guess, as well, because that matters, right? If your bottom piece of tape at the very edge, that's a greater R value to the center of the new piece of, or the top piece of tape. That's going to change your value because your R is greater, so therefore your magnitude is going to be less. And again, as you can see, our lab 1 had a slightly greater magnitude of electric force. And as for which one's more likely to be closer to the real value, lab 2 should be closer to the real value, though obviously we got our gravitational force closer to lab 1. But yeah, lab 2 treats it more accurately.